Hello class, welcome to Geometry Lesson 7.3, Proving Triangles Similar. So our question today is, we want to address how do similarity transformations determine the angle and side length condition necessary for triangle similarity. And our goal today is to use dilation and rigid motion to establish triangle similarity theorems. So we're going to start, there are three similarity theorems that we want to establish and actually prove, and then we're going to apply the examples in some example scenarios here. Now the first one is angle-angle similarity. So if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So you can see that angle A is congruent to angle D, angle B is congruent to angle E. Now if that's the case, remember that one of the definitions, what it means to be similar, is that the sides are proportional, but also that the angles are congruent in both the pre-image and the image. So you can see that if this were, for example, to be 30, and this were to be 80 degrees, for instance, then we can clearly tell that this angle is going to be the same for both triangles because they have to add it to 180. So if we know two angles, then that means we know that the third angle is the same for both triangles, and therefore we can establish similarity. So let's actually go about improving this. So we have two triangles here. We know the two angles are congruent, so angle T is congruent to angle X, angle U is congruent to angle Y. So let's prove that they're similar. So what we're going to do is we're going to transform XYZ to make it look like TUV. We're going to do a dilation. So we're going to dilate XY of the triangle so it's the same measure as that of TUV, and we're going to multiply by a scale factor. So we're going to essentially dilate this by a scale factor. So what we're doing is, if I want to change this size so it's the same size as on this triangle, I want it to be the same size as TU. Well then, for example, if TU were to be 9 and this were to be 3, then the scale factor would be 9 divided by 3, or 3. And so that means I would have to triple the size of XY to get TU, for instance. So this is what we're going to do. We're going to divide those and get our ratio, a scale factor, and then we're going to scale this by that scale factor. If we did that, then we're going to get a triangle that's dilated, it's enlarged, and it appears to be the same size as TUV. And now because you have the sides XY and TU are the same length now, X prime, Y prime now, because for the new triangle, because we dilate it so, then therefore by angle, side, angle, and angle, side, angle, the two triangles have to be congruent. So therefore they are congruent by ASA congruence. Because the two triangles are congruent, then that means that there exists a rigid motion that would map one to the other. In this case, that would be a reflection. If you were to reflect these two triangles about the horizontal line, that would be a rigid motion to get one to the other. And because they are congruent and there exists a rigid motion, then that means, because there exists a rigid motion, that means that there also exists a similarity transformation, because a similarity transformation is a combination of a rigid motion, in this case reflection, and the dilation that we did earlier. Because there exists a similarity transformation, that means that the two triangles are similar. And that's the end of the proof. All right, so for the next theorem, side-side-side similarity, notice that this sounds very similar to side-side-side congruence, the SSS theorem for congruence. However, it works a little differently. Because the triangles are not congruent, they're similar, that means that they're proportional to one another. So if I were to divide the corresponding sides, they would be equal to each other. So if I were to take AB, say 9, and I were to divide it by the corresponding side, DE, which is 3, I would get 9 divided by 3, which is 3. And that would be the same ratio as if I, for instance, divided by AC by DF. So if I took AC to be, for example, 15, and DF were 5, well then 15 divided by 5 would also be 3. And if I do this for all the sides, for all the corresponding sides, and I get the same ratio, then the two triangles are similar. Here's another example. If I want to divide BC by EF, and BC is 6 and EF is 2, then 6 divided by 2 is also 3. And then therefore I can claim that they're similar by SSS. All right, so we're going to go ahead and prove this theorem using what we did earlier. We're going to dilate ABC and enlarge it so that it looks like FEG. So again, like we did earlier, this time we're going to dilate all the sides of ABC so that they're the same length as EFG, the sides for EFG, by multiplying by the scale factor. So for example, if this were 6 and this were 2, if this were that were 6 and this were 3, the scale factor would be 6 divided by 3, which is 2. And that means I would have to double the size of the triangle to make it look like the other one. So I would double all the sides here so that it looks like EFG. And if I did that, I would get a similar look, congruent looking triangle. And now we know that all the sides have to be congruent. And that's because we multiplied by the scale factor, and it was given that the scale factors were the same for all the sides, right? So, or the ratios rather were the same for all 3 sides, and so that the scale factor is the same. And then therefore, the triangles must be congruent. So by SSS, they are congruent side, 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 which means that there is a rigid motion to get from one to the other. The rigid motion is pretty easy in this case. You just have to translate it to get so that they overlap. Now, because there exists a rigid motion as well as a dilation transformation to get from one to the other, that means that we have a similarity transformation in our hands. And because there exists one, that means the triangles must be similar. And that's the end of the proof. All right, and for the last theorem of similarity, it's the side angle side similarity. So for example, if this side AB is proportional to side DE, and the angle in between, the angle here is the same, angle B is congruent to angle E, and then the side BC is proportional to side EF, then that means we have SAS, which means that we can claim similarity here. Let's prove this. So this time we're going to go from this triangle LMN to triangle, in this case, so we're going from triangle LMN to QSR or QRS. And so that means we're going to shrink this triangle. We're going to go from here to here. So if I want to shrink the triangle, I'm going to multiply by the scale factor. So for example, if this were 3 and this were 6, then the scale factor will be 3 divided by 6, or 1/2, since we're going from pre-image to image here. And so I would have to reduce it by 1/2, for instance. So multiplying by the scale factor for both sides, and we know that the scale factor for both sides is equal because that was given, then we're able to get that the triangles are congruent because these 2 sides are congruent. So we got a side that's congruent, side, side. And we know that it was given that the angles between them are congruent. So that means the 2 triangles are congruent by SAS, and therefore there exists a rigid motion to get from one to the other. What is that rigid motion? Well, you can reflect this triangle. So maybe it looks like this when you reflect it. And then you can rotate it and then translate it, and then that will get you from one to the other. Because there exists a rigid motion or a combination thereof, as well as a dilation, that means we have a similarity transformation, which means that these triangles are similar. That's the end of the proof. All right, so now we're done proving the similarity theorems. Let's go ahead and apply them. For example 4, we are looking at, we're trying to determine which theorem to use to show that the triangles are similar. So obviously it looks like we're going to use SSS for this, for part A, but we want to determine if SSS works. So if I were to take this triangle and I were to reflect it about this line, then I would get a triangle that looks like this, and we can see that they line up very well with each other, okay? So if I were to line that up, it would kind of look like this, and there would be 3, 4, and 5. So we can see that the 3 corresponds well with the 4.5, so I can divide 4.5 by 3. 4 corresponds well with 6, so 6 divided by 4. And then 5 corresponds well with 7.5, so 7.5 divided by 5. All right, and then if we divide those, you get 1.5 for all of them, which means that all of the ratios are equal, which means the sides are proportional, which means by SSS, these two triangles are similar. So yes, by SSS similarity. All right, let's look at example 4B. This one does not look as obvious because the triangles overlap. We're looking at this big triangle and we're looking at this blue triangle. So let's draw the big triangle first. Okay, so, and we know that this bottom side is 27 because of the 15 plus 12, and this is 18. Now, this blue triangle is hard to tell whether it's similar to this or not. So what we're going to do is we're going to reflect this triangle about this line. And if we do that, we get something like that looks like this. So that's a reflection about this. You can kind of tell it's a mirror image of this one right here. So that works well. And then if this is 12, then this is 12. If this is 12, this is 12 rather. And so that's what we have so far. And if this is R, then this is going to be my new R or R prime, whatever you want to call it. I'm just going to call it R. All right, so now if I take this triangle, the one in red now, and I rotate it this way, then I'll get one that looks like this triangle, and I'll draw it down above, or down below here. So we have this point, which I'll call P. We have R, and we have Q. Okay, and that's the smaller triangle. It's supposed to look a lot smaller than that, but you get the idea. This one is supposed to be bigger. So in fact, I'll try to draw a little smaller. So let me try to prove that drawing a little bit. Okay, so there's my triangle, and this is point P. All right, and then we know that this is 12 and this is 18 because that 18 was this side and it got rotated downward. So we got these two triangles, and now we can kind of see, okay, they kind of look similar. This is definitely the same angle because they're both angle Q. So obviously they share that angle to begin with. So it has to be congruent. So we know that angle Q is congruent to angle Q because they share it. That's called the reflexive property. And we can show that the sides are proportional. So we know that PQ is proportional, looks proportional to RQ. So let's see if that's true. 18 divided by 12, and we have to see if that's equal to SQ and PQ right here. So SQ is 27 and PQ is 18. So we need to see if that's proportional. And if we were to do 18 divided by 12 here, let's see what we get as a decimal. So 18 divided by 12, that's 1.5. And then if you were to do 27 divided by 18, that's also 1.5. So that means that those two sides they're proportional. And so we got ourselves a side angle side scenario, and therefore the two triangles are similar by side or side angle side rather. Similarity theorem. All right, so we showed that those two triangles are indeed, those two sets of triangles are congruent by the sum of the two of the theorems. Let's find MN in this example. So we know, so we're going to call this X here to find MN. And we know that these two triangles are similar. How do we know that they're similar? Well, we know that these two angles are congruent. And that's because they're vertical angles and they must be congruent. But you can also, and then we also know that these two sides are congruent to each other, but we can tell that this side is proportional, or is proportional to this side, just like this side will be proportional to this side. So we got a side angle side. Those two sides must be proportional because if you think about it, these two sides are congruent, these two sides are congruent, so they're really proportional to each other. So like, for example, if this were equal to 10, this were equal to 10, this were equal to 5, this were equal to 5, well then 10 divided by 5 is 2, and 10 divided by 5 is 2. They're equal to the same fraction, so they are proportional to each other. So these are similar by SAS similarity. Now that we established that they're similar, that means that we can use proportionality to help us to find the missing side, MN. So X here is clearly proportional to 10, if you were to look at those two triangles. So X is to 10 as, and you can clearly see that 75 here is proportional to this 75 right here, or this number right here, right? So, but we know that this number is 1 because this is 1, okay? Because they're congruent. So 75 is to 1. So X is to 10 as 75 is to 1. Rather, it should be the other way around. 75 X is to 10 as 1 is to 75. You got to do it in the same order. So this is for the small triangle, and then this is for the large triangle. So you got to do it in the same order. All right, so we can cross multiply here, and to solve this equation, this is a proportion. So we get 75x equals 1 times 10 is 10. Then we can divide by 75 on both sides, and we now have x. We can divide this by 5 to reduce it, and that'll give us 2 over, and here we have, should be, let's see, so 5 goes into 7 one time, so about 15, so it'll be 2 over 15 for x. All right, so let's look at another question. Now this one looks similar to the one that we did earlier, where we were looking at the two triangles, and then we had to do some kind of like reflection, right? When we had to reflect this, and then kind of like rotate it, we had to do that whole thing. Or rather, this one, we could do this one. So we can reflect this so that it looks like this, right? And then we can rotate it, and it will look like that triangle, right? So, and this side is, let's see, let's draw the big triangle. So this big triangle is FGH, and this small one that we did, so this is going to be my new J because it reflected. So this is J, and this is F because it just got rotated down, and this is G, got rotated down. So looking at this diagram, it seems that because F is congruent for both of these, it seems that triangle FGJ is similar to FHG. And we kind of showed this with that other example. These two triangles are going to be similar, and this is the similarity statement. And you can kind of see that based off of the transformations that I've shown here. All right, so now that we established that the triangles are similar, those triangles there, we can use the similarity statement to help us here, or we can use the diagram. So FG here is, or rather this FG, let's see here, is this is actually 30, and this right here, this JH here is, we're trying to look for FG, so let's, or rather we're trying to look for FJ, so we'll call this X. So that means this here is X plus 32 in the big triangle. So this big triangle, this side right here, is a total of X and 32. All right, so we got our triangle, our two triangles. Let's go ahead and set up our proportion. We know that x, so we know that we want to also set up x. This is x right here. So actually, let me draw this so it's clear. This is x. I'm going to draw this a little clearer. And then this is the big one. I'm going to draw this big. So we can kind of see. Maybe I should draw this smaller. And this is x plus 32. This is 30, and then that's x here. And this is 30 right here. Okay, so we can set up our proportion. Now I will erase this. So we have here that x, which is this one right here, looks like 30, as this 30 right here looks like x plus 32. And so now we can set up our, we can solve this. Remember, we cross multiply here. Now at this point I can erase this diagram because we don't need it anymore. It was just to visualize these sides. Let's go ahead and solve this. So if we solve this, we have x times x plus 32 equals 30 times 30 is 900. Then we distribute x here. Then we subtract 900. This is a quadratic equation. And so we want to set one side equal to 0. So let's do that here. So we're going to subtract both sides by 900. Now I'm going to solve this quadratic equation by doing the factoring method. In order to factor this, I need to come up with two factors of 900 that add up to 32. So I'm going to come up with my x, what I call an x table, and I'm going to figure out two numbers that multiply to this number but add up to this number. This is 32. And so I need two numbers that multiply to the top, add to the bottom. And this is the part that you're going to need a calculator to divide the two numbers. So if you were to take, for example, 900 divided by 30, you're going to get 3. 900 divided by 30 is 30. And we know that 30 plus 30 is 60. So in this case, you can't get two numbers that work out for that. So you're going to have to come up with two numbers that multiply to 900 that add up to 32. And so I would suggest doing this on the calculator, getting some numbers. So for example, another example could be 900 divided by 50 is 18. And so we know that it has to be negative 900. So if I were to make one of these numbers negative, then I can get 32 from this. I would have to make 18 negative because 15 plus negative 18 is 32. And 50 times negative 18 is negative 900. So once we find out those two numbers, which I know I found it pretty quickly, that just happened to be my second guess, we're going to factor this. So we have x plus this number and x minus this number. All right, and the next step to solve this by factoring is you want to set each of these equal to 0. So we're going to solve this. So the only way to get that to be 0 is when x is negative 50. The only way to get this to be 0 is when x is 18. So we got two solutions here. Clearly, the negative 50 solution doesn't make any sense because we're talking about the side of a triangle. So therefore, our only solution has to be 18. So we can claim that fj is equal to 18, and that is the end of our solution. All right, I hope you found this useful, guys. I hope you found this informative. Hope you took a couple of things. And as usual, I'll see you in the next one.